All right, well, let's go ahead and get started, everyone. Thank you for coming to the LPI virtual seminar this week. Our guest this week is Dr. Tasha Dunn of Colby College. Dr. Dunn is an associate professor there, and previously an assistant professor, previously assistant professor at Illinois State University. Her talk will be on to be a CK or not to be a CK, the unusual case of Northwest Africa 10588. Just as a reminder of our format, we will be answering questions in the last 15 minutes of the talk. If you have a question during the talk, please feel free to type it into the chat, and then I will read it off at the end. Please make sure your microphones are muted and cameras turned off during the talk. With that, I think we're good to go. Let's go ahead. Please take it away, Tasha.
Okay, thanks, Sean. Appreciate the introduction there. I'll go ahead and get started. I don't see my face popping up here. I hope everybody can see me. So thanks so much for the invitation. I'm excited to talk to this group. Some of you know me, so many of you don't, but I teach at Colby College, which is a small liberal arts college in Waterville, Maine. And so when I give talks, one of the things that I like to do is to talk about student projects and highlight some of the things that our undergraduate students are doing here at Colby. We of course don't have graduate students, but we do have really capable undergrads, and occasionally we have really exceptional undergraduate students who can do really incredible work. And so I'm going to talk about one of those projects from this summer. This is very new. This is the first time I've presented this data, so I'll be excited to hear what you all have to say. But this is a story of NWA 10588, which was classified as a CK chondrite. So let me start, get my screen to move here. All right, so let me start by just a little bit of background information. I imagine most of you know this, but in case we have some other people in the audience who don't, I think when most people think of meteorites, they probably imagine something that looks like this, which is an iron meteorite. Iron meteorites come from the cores of differentiated planetary bodies. And so those are bodies that have been heated up and melted and chemically differentiated into a core, a mantle, and a crust. We get lots of other really interesting meteorites from differentiated planetary bodies like pallasites, for example, which we believe to represent the core mantle boundary. So olivine from the mantle and metal from the core, which I think is super fascinating to think that we actually have a way of sampling that specific boundary in a planetary body. That's really great. And then lots of really wonderful achondrites that many of you work on that come from the crustal material of these bodies. And so these are the howardites, eucrites, and diogenites from the HED group, which is from asteroid 4 Vesta, which is shown right here. So all the terrestrial planets and the moon are differentiated into those chemical layers. But most meteorites actually don't come from bodies like that. They come from smaller objects in the asteroid belt called asteroids. Here are a few examples of what asteroids look like. Some people are sometimes surprised to know that they aren't spherical objects. Most asteroids are too small to be spheres. Only a couple like Ceres and Vesta have reached the size to be spherical bodies. So a lot of material in the asteroid belt, but it's very big. It's 3 AUs wide. So lots of space between material. You could stand on one asteroid and not see another. So it's not like you see in the movies when someone's flying through the asteroid belt and they're having to dodge material right and left. It's pretty calm in the asteroid belt, but lots of primitive objects there. And so we call these asteroids primitive because they contain the oldest solar system material. So the oldest solids in the solar system. So these are things like calcium aluminum inclusions, chondrites, which are spherical droplets of silicate minerals, and then matrix material and metal, which kind of fill in the gaps between all those other types of material. So these primitive asteroids are really important to us because in many ways they're like windows into the solar system's history. It allows us to see what the solar system was like very early on before these planetary bodies ever formed, right? So Earth and the other terrestrial planets were made of this chondritic material initially, and then that melted and became layered. But lots of primitive asteroids are floating around, so we have that material to study. And so the meteorites that are derived from primitive asteroids are called chondrites. They get their name from the word chondrules, which comes from a Greek word meaning seed, because they're round spheres. So even though these primitive asteroids haven't been affected by melting, it doesn't mean they didn't experience any secondary processing. So there are certainly things that have happened to this material in the last 4.5 billion years. One thing that happens to a lot of objects is that they have been affected by impact events. Impact events were especially common in the early hundreds of thousands of years of the solar system. So some things that can result from impact events: shock metamorphism, for example. That's a high pressure, high temperature, but very short-lived metamorphism in a sample. Melting can sometimes take place as well. Now, not large-scale melting like you would see in a differentiated body, but smaller regional melting leading to things like melt pockets or melt clast. Brecciation, meaning that you take an object and you break it up into angular sized particles because of the impact events. And then sometimes brecciation will actually lead to or be combined with mixing. And so mixing occurs when two asteroids will collide with each other. If it's a low energy collision, that material can often be brought back together after that collision, after that breaks it apart. And so then you get material that's mixed together, like this sample here, which is an ordinary chondrite that has a little piece of something else right in the center of it. So it's very obviously something that came from somewhere else, some kind of xenolithic type of material. And I find these to be really interesting, and I've gotten super interested in them in the last probably 3 years or so. And they're really great for undergraduate projects to, identify the clast in the object. So those are fun, and it always gives us some kind of information about that period of the Great Bombardment and early solar system formation. So another type of secondary process is aqueous alteration. Aqueous alteration is a change in the composition and the mineralogy of a rock due to interaction with water. This happens mostly in the carbonaceous chondrites, and I'll talk about what that means in a little bit. But carbonaceous chondrites, we think, probably formed in the outer part of the solar system where it was much colder. And so because of that, they probably had ice on the surface. That ice could have been eventually melted, and that's where we get the water from. And so just like rocks on Earth, when they interact with water, it changes the mineralogy, changes the texture. This is a chondrule that's been unaltered, and then here is a picture of an altered chondrule, and so you can see it looks very, 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 very differently. So it has been changed significantly by that interaction with water. I always think of cold miser here down at the bottom when I think of aqueous alteration, and heat miser when I talk about metamorphism, which is what I study. But aqueous alteration is a very complex process. It's not a thing that I study specifically, but it happens in a lot of carbonaceous chondrites. But like I said, that process that I study, that I like to look at the most in chondrites, is metamorphism, which on Earth we would refer to as a change, like a recrystallization that's driven by heat and pressure. Now, asteroids are very small, so pressure is negligible. So this is a heat-driven process. So we call it thermal metamorphism when we talk about metamorphism on asteroids. And so at the top here, that's heat miser. So we've got cold miser for our aqueous alteration, and then heat miser for metamorphism. So if we imagine that we start off with an asteroid that looks like this is a primitive asteroid with our chondrules and CAIs and metal and matrix material. The source of heat for that metamorphism, most people would agree, is probably the decay of aluminum-26. And aluminum-26 is a short-lived radioactive isotope, has a half-life of about 700,000 years. And so that means it could produce heat for probably about the first 14 million years of the solar system's evolution or so. So it's a very, very early type of process. When you heat up a body due to the decay of aluminum-26, what happens to that body is that it develops what we call an onion shell structure. And so it's called an onion shell because it looks like it's an onion. So you have layers here. Now, those are not compositional layers. Those are layers that represent increasing degrees of metamorphism. And so it's most metamorphosed in the center where the heat was kind of regulated, right? Kind of constrained, I guess, contained in the center of the object. And then it's less metamorphosed as you go towards the exterior, as that heat would have escaped into space. And so we have varying degrees of metamorphism within the object, and that's why we call that an onion shell. Now, chondrites, we can look at and we can determine how metamorphosed they were. And we've developed a scale for describing that called petrologic type. And so you'll see this is a scale that ranges from type 3 to type 6, with the type 6 material being the material that's in the center of the object, and then it goes 5, 4, and 3 is closest to the exterior. So that's the least metamorphosed, and then grading into the center, we have the most metamorphosed. And so we determine those petrologic types based on changes in the extent of recrystallization or geochemical changes like the extent of olivine homogeneity that I'll talk a little bit more about later in the talk. If you are wondering, if you're not a person who studies chondrites and you're wondering what happened to type 1 and type 2, that's actually how we describe aqueous alteration. So it's a kind of a strange scale that grades from aqueous alteration into thermal metamorphism. So petrologic types 3 can actually be divided into subtypes 3.0 to 3.9 because that material is very sensitive to metamorphic change, and that will be very important later on in the talk. We'll be looking at that. Okay, so let's talk a little bit about chondrites and how they're classified and why that matters to us, and in case you need a little bit of a refresher. So there are 3 different classes of chondrites: the carbonaceous, ordinary, and instantite. Carbonaceous chondrites are by far, ordinary chondrites are by far the most prolific of all chondrites, and most of what we know about metamorphism in chondrites we've really learned from ordinary chondrites. Instantite chondrites are made primarily of the periodic mineral instantite, and they formed under very reducing conditions. Carbonaceous chondrites can be divided into several groups, as you can see here. The name carbonaceous is a bit of a misnomer. They're not very carbon rich, with a couple of exceptions like the Ci carbonaceous chondrites, which are the most primitive of all the carbonaceous chondrites. But that name is stuck over the years. So several different groups of carbonaceous chondrites, but these are all primitive compared to the ordinary and the instantite chondrites. Like I said a minute ago, carbonaceous chondrites are mostly aqueously altered. Many of those groups have experienced significant amounts of aqueous alteration. But then there are 4 groups of carbonaceous chondrites that have been metamorphosed: the COs, the CVs, the CKs, and then the CHs. And the CHs are a strange little group, but the COs, the CVs, and the CKs have metamorphism that's really very similar to what we see in the ordinary chondrites, but at much lower levels. The CV and the CK chondrites are so similar that they've been described as a clan, which means that they come from the same part of the solar system, and that explains the isotopic and chemical similarities between the two. So CK chondrites, let me tell you a little bit about them, since we'll be talking about the CKs and the CVs today. Compositionally speaking, they're a very highly oxidized group of carbonaceous chondrites. In fact, the most oxidized group of carbonaceous chondrites. And so that means they contain a lot of very nickel-rich phases like sulfides and oxides, and they even contain a lot of nickel in the olivine, which is an interesting characteristic of the CKs. Petrographically speaking, they are very matrix-rich samples, and so you can see a few images here on the right-hand side. And this actually grades from a CK3 at the top to 4, 5, and then 6 at the bottom. So you can see some of those petrologic or textural changes that are happening during metamorphism, but a lot of matrix material compared to chondrules. The chondrules are relatively large. The average sizes are around 700 to 800 microns. One of the things that's interesting about chondrules in the CK chondrites, however, is that the rims are absent. There's such a thing called a fine-grained rim that is thought to be accreted dust, so dust that accretes on the outside of chondrules. We see those in a lot of different chondrite groups, but we don't really see those very much in the CKs, which makes them unique. And refractory inclusions, the calcium aluminum inclusions, are also relatively rare. You can see one right here, one big one in that CK3, but then you don't see them very much after that, probably because they've been metamorphosed. But refractory inclusions are pretty rare. But the thing that's the most interesting to me about the CKs is that they exhibit the full range of thermal metamorphism, all the way from petrologic type 3 to petrologic type 6. And in that way, they are really nearly identical to the ordinary chondrites. And I studied ordinary chondrites in grad school, and so it seemed like a logical next step to study the CK chondrites. Another really important thing about metamorphism of the CK chondrites is that all of the type 3 CKs, which are the least metamorphosed, are actually relatively well metamorphosed. And so they're high petrologic subtypes, so subtype 3.7 or higher. So we don't have any material that's a CK that's not highly metamorphosed, which will be important. So the CV chondrites, they're a slightly more complex group. CV chondrites, as you can see over here, are divided into oxidized and reduced groups, depending on the conditions they formed under. So we've got reducing conditions versus oxidizing conditions. And so one of the ways you can tell them apart is that reduced CVs contain more metal than magnetite, whereas oxidized CVs contain more magnetite than metal. They would also contain those nickel-rich sulfide phases though. So to make it even more complicated, oxidized CV chondrites are divided into a Yinde type and Bally type. And so those are two different kinds of aqueous alteration. Bally type CVs are more altered than a Yinde type CVs. It's a metasomatism even. And so there are some mineralogical differences between the those two samples that are attributed to differences in aqueous alteration and the extent of aqueous alteration. However, there was a recent paper that just came out last year by Gattacia, maybe I'm probably saying his last name wrong, and I apologize, but it came out in 2020 that suggested that the oxidized CV chondrites were actually all the same, and that there's really no significant difference between the Yinde type and the Bally type other than the extent of metamorphism. And so the Yinde types being more metamorphosed than the Bally type. And so they suggested that we should abandon that classification scheme, which makes it a lot easier. So I'm kind of glad that was their suggestion. And then we just stick with the oxidized versus the reduced CVs. So CVs petrographically are a little bit different from the CKs, as you can see from this image here. There are a lot more chondrules in the CVs than there are in the CKs. And so there's a similar abundance of chondrules and matrix. The chondrules are about the same size. They can be a little bit bigger in the CVs on occasion, but 700 to 800 microns is still about the same size as the CKs. We do see a lot of fine-grained rims around chondrules, and if you look closely at some of the chondrules in this sample here, and I'll kind of point to some where I can see it, but there are some fine-grained rims around many of these chondrules, and so you do see that, and again, remember that's relatively absent in the CKs. Refractory inclusions are also very common in the CV chondrites. In abundance is usually around 10% or so, sometimes a little bit higher than that even. And a Yinde is probably the most well-studied chondrite of all, certainly probably the most well-known carbonaceous chondrite, but it's been extensively studied. It was a fall, and we have a lot of material from it. And so most of what we know about calcium aluminum inclusions, we've learned from the Yinde meteorite. Another important thing about the CVs is that they have relatively low petrologic types. So 3.3 are lower than that. Okay, so what does all of this mean? Well, the CVs and the CKs are so petrologically and isotopically similar that Greenwood in 2010 argued that they originated from the same asteroid. He suggested that that asteroid was a thermally stratified asteroid, so basically an onion shell model, where you have the CK material, the CK onion shell, basically surrounded by CV material. And now that would make sense because remember the CV chondrites are less metamorphosed than the CK chondrites, so they would then be closer to the surface than the CK3s. If that is true, then there ought to be a single metamorphic sequence between the CV chondrites and the CK chondrites. Now, Greenwood suggested that the CV-reduced chondrites was probably the best precursor material for CVs and CKs, though they didn't propose an exact precursor or an exact sequence, but suggested that it was probably something similar to the CV-reduced. And so then they suggested then that you would go from CV-reduced to CV-oxidized A specifically, and then to CK from there. Now, in the Greenwood study, they argued that you could not make CK chondrites from Bally type CV chondrites because the oxygen isotopes in the Bally type CVs are heavier than they are in the CKs. And that is not what you would expect to see if you dehydrated a phyllosilicate bearing rock. And so they suggested that the CVBs, the Bally-like CVs, were very different from even the CV reduced and the CV oxidized samples. And so that metamorphic sequence would then probably look something like this. One of the problems with that, though, is that it would require a significant change in oxidation state to go from the CV reduced to the CV oxidized and then the CK chondrites in the same parent body. And again, it's during metamorphism, something would have to happen so that you have that change in oxidation state. And we looked very specifically at the magnetite and just didn't see really how we could reconcile that taking place in that one parent body. Now, let's say hypothetically, this new study that suggested that the CVs are from two different parent asteroids, the CVs reduced body and a CV oxidized body, then that would mean that there are two other possible metamorphic sequences. So one metamorphic sequence where you take CV material, CV oxidized material, and metamorphose it to make the CKs. And then another sequence where you take CV reduced material and metamorphose it to make the CKs. Now, this second scenario would still require a sudden change in oxidation state to go from reduced to oxidized. And this first scenario is complicated by the fact that Greenwood says isotopically you can't take a CV oxidized B, a Bally type CV, and turn it into a CK. So each one of those potential sequences is not without, a small problem, but this is consistent with the early studies of the CVs, like work by McSween, like in 1977, for example, and then Gimmon years later, who suggested that there were two different metamorphic sequences, one for the CV reduced and one for the CV oxidized. So that's a little bit more consistent. So how do we determine petrologic subtypes for chondrites? Well, we use things that we call geochemical indicators of metamorphism. And one of the best geochemical indicators of metamorphism is the homogeneity of olivine. And olivine becomes more iron-rich and more equilibrated during metamorphism, particularly at the low petrologic types from type 3.0 to 3.9. There are changes in minor elements like calcium and chromium as well, but that's just one example of a geochemical change that we can monitor, and we can use the extent of that change to say, okay, well, this is a sample that's been metamorphosed to type 3.5 or 3.8 or 3.2, whatever it happens to be. And so based on the homogeneity of olivine and other geochemical indicators like pyroxene, the abundance of metal, sulfides, etc., it's been suggested that the CV chondrites are less than petrologic type 3.3. Now there was a recent study, I think it was in 2006 by Bonal, that looked at organic matter in the CVs and suggested that they were actually more metamorphosed than the silicate minerals would suggest. And so, for example, they said a Yinde was a 3.6, whereas a Yinde here I think is a 3.2 or a 3.3. I don't think that organic matter is really a great measure of how metamorphosed the sample is, and so I do tend to think that the CVs are less metamorphosed than that. And then if we look at the CKs, most CKs are type 3.8 or 3.9 based on silicate mineral equilibration. And then we have one sample that's been discovered, NWA 5343, that is a petrologic subtype 3.7. But what this means is that we don't have a complete metamorphic sequence between the CVs and the CKs because there's kind of a gap between petrology type 3.4 and petrology type 3.6 because we don't have anything at that particular subtype. So where did that material go? So one of the big questions is there some kind of material somewhere that's transitional, or that's basically between a CV chondrite and a CK chondrite? So it would be in that petrologic type area that would make a single metamorphic sequence between the two make a little bit more sense. So interestingly, I got an email from Alan Rubin last spring. Alan's also been interested in the CV and the CK chondrites, and he had a sample that he had classified years ago, NWA 10588, that he was hoping that we could take a look at and study in a little bit more detail. And so this particular sample, this is a transmitted light image of the thin section, was classified as a CK3, but Alan described it as being intermediate between normal CV3s and typical CK4s. And that was based on two observations. The first observation was that it had a CV-like matrix, meaning that it had a very fine-grained matrix, which is characteristics of the CVs. But the olivine in this sample is relatively well equilibrated, so it has a high Fa-like content and equilibrated to extents that is consistent with the CK chondrites. So it's got CV-like characteristics and it's got CK-like characteristics. And so Alan suggested that perhaps this is some kind of transitional material between the CVs and the CK. So maybe it's that branch, that transition that we're looking for. So in this study, what my undergraduate student worked on this summer was to really try to answer the question, is this a CV, is it a CK, or is it transitional between the two? And so we undertook a detailed petrographic and mineralogical study to try to answer that question. So we used a scanning electron microscope for a lot of this. We used the SEM at Bowdoin College, which is about 45 minutes down the road. And so using the SEM, we made X-ray maps, identified the minerals that we would expect to see, of course, took backscatter electron images of areas of interest. And then a few weeks later, went down to Washington University in St. Louis to use their electron microprobe. And so there we analyzed olivine, pyroxene, oxides, and sulfides. And olivine, oxides, and sulfides are particularly important phases for addressing this question of whether a sample is a CV or a CK, because they are very different in the CV and the CK chondrites. So let me talk a little bit about the petrography of this sample then. It's a really pretty sample. I will say that when I saw it in thin section, I immediately thought it looked like a CV chondrite. So that was an interesting thing about it. This is a part of RGB map of the thin section. So this is kind of in the middle. And this RGB that corresponds to magnesium, calcium, and aluminum. So you can see it's a very magnesium-rich sample with a lot of olivine and pyroxene, but dominantly olivine. If we talk about the chondrules a little bit more specifically, there's about 65 to 70% of the sample will consist of chondrules. They're mostly PO and POP. If you're not familiar with that terminology, that's porphyritic olivine and porphyritic olivine pyroxene. Most of the chondrules range in size from about 600 to 800 microns along the longer axis, because these are all slightly elliptical. And the average size is 886 microns. And so to illustrate what I mean by they're a little bit elliptical, if you look at like any of the chondrules in this view here, of which of course there are many, you'll see that many of them are longer in one axis than they are in the other. And that long axis tends to be along the horizontal where this image is. And so they're elongated in that horizontal direction. That's called a petrofabric, and that is a thing that's actually pretty common in the CV chondrites. It's not as common in the CKs and other groups, but you do see it in some other chondrites as well. And that's been associated with either a burial or shock events on the parent body that make everything a bit elliptical. So the matrix, let's zoom in on some matrix and take a look. Here are a couple of images I'm going to show you of the matrix material. You'll notice, in fact, that it is very fine-grained, as was initially observed by Alan Rubin and his co-authors in the classification. Lots of different shades of gray, indicating that you have lots of unequilibrated phases, silicate phases in the matrix, and then some bright areas as well. So those would be oxides or sulfides. Here's another image of the matrix, and again, just illustrating how fine-grained it is. So it is a very, very fine-grained sample or matrix, which is why it appears to be black in that transmitted light image. Let's see. So this sample is also pretty well shocked and also heavily weathered. And so the shock scale on this is an S4, which is pretty high. But interestingly, most CVs and CK chondrites are highly shocked. They're the most shocked of all the chondrite groups, which is a thing that is unique about them. And so as a result of shock, one of the things that we see in the sample is a lot of fractures that we would associate with the shock event. You can see many of them here. These are some of the bigger ones. It's interesting to me that they are also aligned in that horizontal direction along the long axis of the chondrules. They're pretty big. These are pretty big fracture zones here, or fractures, I should say, in the sample. And you can see some of these fractures actually cut through chondrules, and then there are fractures that go around chondrules, which I think is an interesting observation. Like I said, though, this is also a very weathered sample, and the bright stuff in the fractures, which I thought initially would probably just be a sulfide, like iron sulfide, is actually limonite. And so this is a weathering product. And so these products, or sorry, these chondrules, or this chondrite, has been weathered, so it sat on the surface of Earth for quite some time in the desert. It's pretty common in desert rocks. And so these fractures have been filled with that limonite weathering material as the water went through the sample. So some interesting shock features. Here's a couple of close-up images just to illustrate what I'm talking about here with the shock. Here's a fracture that cuts through two different chondrules. You can see it going right through those two chondrules there. It's partially filled in with limonite. And here's a chondrule at the bottom, and that fracture has actually split and gone around that particular chondrule. And it does that in a couple of places. I think that's really interesting. It reminds me a lot of streams when they diverge when going around something with high topography. Not to suggest that that has high topography, but it just reminds me of that. And I think that's an interesting thing to see. This is an olivine grain here on the right, very heavily zoned olivine that has been offset by what is probably shock, right? And so there's a area here and then an area here where you see some offset in that grain. It looks very much like a fault from the surface if you were looking at something on the earth, but that is likely attributed to the shock as well, though that's a strange thing, and I haven't seen a lot of that in chondrites before, but that's a thing that's unique and I think worth looking at in a little bit more detail. So some interesting effects of the high shock level in this sample. All right, let me tell you a little bit about the chondrules in this sample. Almost half of all chondrules are porphyritic olivine pyroxene chondrules, so it has olivine and pyroxene. This is chondrule 18, which has subhedral olivine and orthopyroxene. The olivine is zoned, the pyroxene is not zoned. The average composition of olivine is phthalate 20, and orthopyroxene is incitite 95, ferrocylite 4.4. Here's another porphyritic olivine pyroxene chondrule where you can see the difference between the olivine and the pyroxene a little bit better. The pyroxene is more lath-shaped, and the olivine is just like more diamonds or squares. This is also zoned. We didn't get probe analyses of the phases here though, but according to the SEM, the pyroxene is incitite 71, and the olivine is phthalate 17. And there's a lot of mesostasis in this sample too, which is one of the reasons I wanted to show you this chondrule. Mesostasis is mostly glass with low calcium pyroxene crystallites, and that's common in a chondrule that's been that's poorly equilibrated, so hasn't been equilibrated very well. Here's a porphyritic olivine chondrule. The porphyritic olivine chondrules have really well zoned olivine, and so you can see the zoning here goes from about phthalate 5 in the core to phthalate 22 on the rim, and you can see how the rims have that bright edge around them. That's the zoning in the olivine. These also have abundant mesostasis. The average composition of olivine in this chondrule specifically was phthalate 12. This is a porphyritic pyroxene chondrule. About 15% of all the chondrules were porphyritic pyroxene chondrules. They differ from porphyritic olivine chondrules in that there is very minimal mesostasis. So you can see a couple of areas here I'll point to with my my little mouse here where you have mesostasis material, but it's not anything like what you see in the olivine chondrules. So lots of large interlocking pyroxene grains. The pyroxene here is relatively well equilibrated with an average composition of incitite 90 and ferrocylite 9. And that was from 6 different probe analyses in that chondrule. This is a barred olivine chondrule. It's a little blurry on the image, I apologize. And there were a few chondrules that fell into this category. So you have the barred olivine, abundant sodium-rich mesostasis. The olivine here had a slightly higher phthalate content, phthalate 37, though that was an SEM value. And then lastly, granular olivine chondrules, which is again about 6% of all chondrules. So granular chondrules are very fine grained. You do see a lot of these in CK chondrites, so that's pretty common in the CVs and the CKs. It has some sulfide around the edge, though I don't know if this is a partial sulfide rim or if it's just kind of an interesting distribution of sulfides and oxides. It's probably the latter. And then the olivine in this chondrule is also well equilibrated as well, phthalate 38. This is an unusual chondrule that's a grain, a single grain of pyroxene surrounded by a very large rim. So that's the only sample that we found here where you can see a real significant rim on that particular chondrule. So in terms of composition, so here is what the olivine and the pyroxene looks like. Olivine ranges from phthalate 2 to phthalate 38 with an average composition overall of phthalate 22. We analyzed 13 different chondrules for olivine, and the average composition of those chondrules range from phthalate 11 to 33. So there's a range in equilibration. Here's the composition of the low calcium pyroxene, which is all incitite, an average of ferrocellite 11. And you can see you have a wide range of values, but it tends to be kind of clumped together in a way that's a little different from the olivine. So it's a little bit more equilibrated in the pyroxene. So just to illustrate what these minerals look like in minor elements, so beyond of the phthalate and ferrocellite values, you can see here's a core and rim analysis of an olivine grain from chondrule 25. There's really not a lot in this olivine other than magnesium, silica, and iron, which is a bit unusual for both the CVs and the CKs. There's a little bit of manganese, but beyond that, very little nickel, very little chrome, very little titanium, very little calcium. So it's a pretty pure olivine, if you want to use that word to describe it. Low calcium pyroxene is pretty similar. There's some high chromium content in the pyroxene, and that's probably the only thing that stands out to me as being unique about the pyroxene compositions. They're also low in nickel and titanium, for example, too. So sulfides and oxides. The sample was, again, very weathered, so it was hard to get good analyses of oxide in particular. And we surprisingly didn't find very many sulfides. We actually only got an analysis of 2 sulfides, and we looked for a very, very long time. They're both troilite. One has about 2.5% nickel, and the other has about 0.3% of nickel. It's a little bit of chrome, a little bit of molybdenum, but that's basically just FeS. So those are troilite grains. But sulfides and oxides, they're in the matrix, they're in some of the chondrules, just kind of poking around. But just not in very, very good shape. Here's the largest of all of the oxides. It's kind of at the top of the sample. It's a pretty big sample, but again, even on this sample, this particular grain, it was very hard to get good analyses, and we got, I think, 5 analyses just from that single grain. This is one of them here, magnetite 2. So you'll notice that the totals are a little low. Those are the best totals that we got. For the oxides, again, it's really weathered, so it was hard to get an analysis near 100%. But the olivine also very much, the magnetite, much like the olivine, is just mostly iron and oxygen. There's a little bit of silica and a little bit of sulfur, probably from some degradation or contamination. But there's no nickel, there's no chromium, there's no titanium, there's no calcium, no vanadium. So there's not really anything else there, which is strange for the CV and the CK chondrites. Here's an example of a single chromite grain that we found. You can see it's also a little bit low in totals as well. Okay, so let's get to the good stuff though. What does this tell us about the sample, and is it a CV chondrite, is it a CK, or is it transitional between the two? So let's examine the things that we've looked at. So we'll start by looking at the matrix, since that was one of the initial characteristics of the sample that was particularly unusual. And so here is NWA 5343, which is a CK 3.7, and here's Vigorano, which is a reduced CV chondrite. The resolution of these images is not exactly the same, but you can certainly see that there is a big difference here between the two. CK chondrites are recrystallized, so you have large crystals of olivine and pyroxene, mostly olivine. It's well equilibrated in the matrix, the olivine and the pyroxene. Vigorano, very fine grain, submicron size specifically, and you can't see it, of course, but the phases would be unequilibrated. So what does our sample look like? Here's a reminder. This is one of the images I showed earlier of the matrix. This is at the same scale as this image here of the CK. And so I did that on purpose so you can compare the two. And you can see very clearly that this matrix here is certainly much, much more fine-grained than what is typical of the CKs. So this is in fact a CV-like characteristic. So this is what you would see in a CV chondrite. What about the phthalate content of olivine? That was the other thing that was unusual about the sample. On the left, here are some examples of what olivine looks like in the unequilibrated CKs, and here is olivine in a couple of oxidized CV chondrites. Reduced CV chondrites basically look the same. And here's our sample, and you'll notice very obviously that it looks very much like olivine in a CK chondrite. The average composition of the olivine, the deviation, the percent mean deviation of the olivine is consistent with basically a type 3.8 CK chondrite. So that's a CK-like characteristic. But what about minor element compositions in the olivine? That wasn't a thing that was really looked at very specifically initially. So here is an example showing chrome and titanium relative to iron. And iron, of course, is basically the same thing as phthalate content, or works the same way, right? And so that's a measure of the degree of metamorphism. So what I want to point out here is that there's really not a significant difference between the chromium content in the CVs and the unequilibrated CKs. The range is from about 0.5 to 0, right? Kind of falls mostly below this line right here. They plot over here, or our sample does, 10588, kind of plots in the middle of the diagram, but that's because it has relatively high iron content. And the same thing is true for titanium. There's really not a significant difference in the abundances of titanium in the CVs and the CKs, but our sample plots here because it has high iron content. And that is true for aluminum and for calcium. Most of the other minor elements in olivine are not really good for distinguishing between CVs and CKs. The exception to that is nickel, and the nickel content of olivine in the CKs is significantly higher than in the CVs. And so you can see that here. These are the unequilibrated CK chondrites. These are equilibrated here. So there's actually an increase in nickel content in chondral olivine during metamorphism in the CK chondrites. In the CV chondrites, nickel content is very low. And so you can see that NWA 10588 has nickel abundances in olivine that are consistent with what we see in the CV chondrites. So that is something about the olivine that's actually consistent with the CVs and not the CKs. What about compositions of magnetite? I thought this really answered the question right off the bat because it's such a good way to distinguish between the different groups. So here's titanium versus chromium, and here's nickel versus chromium. And you'll see that the CV chondrites are very low in titanium with a wide range of chromium typically. And then we have very different values for titanium and chromium in the CKs, much higher for both. So that's very CV-like. The nickel content here, you'll see the range of nickel is also a little bit more consistent with the CVs than it is with the CKs, or at least particularly with the CK3s. It's a little too low to be a CK3. So pretty consistent with the CV chondrites, but has very, very, very low chromium, which you can see in this figure and in this figure here. So though titanium and nickel are consistent with CVs, the chromium content is anomalous. And so that would be an anomalous feature if this is a CV chondrite. But everything else is CV-like. So what about petrography? Here are some values from the Atlas of Meteorites by Monica Grady. 4 different aspects of the petrography of the CVs versus the CKs. Again, the big difference is the matrix and chondral volume. And as I indicated earlier, this particular sample does have a matrix and chondral percentage that is much more consistent with a CV than a CK. It is a little different, of course, in that it has, we didn't see any CAIs and any metal. So that's kind of a weird thing there. But the matrix and the chondral abundance is definitely more CV-like. If we look at that in a little bit more detail, here is some data from the Gattaca paper from 2020 showing the differences in matrix abundance, nickel content in sulfides, metal abundance, etc., between the oxidized CVs and the reduced CVs. And so are there significant differences between those two groups? And if we were to compare our data to these last 2 lines of data here, this is very much consistent with what we would see in a CV reduced chondrite. So 40% matrix, that checks out. Very, very low nickel content in the sulfides, that checks out. Again, the metal would be a little strange. And the diameter of the chondrals, remember our average was 868. They came out with an average of 860 microns for the reduced CVs. So petrographically, with the exception of metal abundances, it looks like a reduced CV chondrite. So is it CV, CK, or transitional? Well, most of the characteristics of this sample are CV characteristics. So matrix abundances, chondral abundances, the fine-grained nature of the matrix, the nickel poor sulfides, oxides, olivine, that's all what you would expect to see in a CV reduced chondrite. The only thing that's really like a CK is the phthalate content of olivine. But remember, that's affected by metamorphism. A couple of anomalous characteristics here, the chromium poor magnetite, that is not what you would expect in a CV chondrite. And the absence of metal is also not what you would expect in a CV reduced chondrite. So that is a little bit strange. But I think that this is a CV3 anomalous chondrite, with the anomalous characteristics being the magnetite and the absence of metal. So what does all of this mean? And I know I'm running a little bit of low on time here, but very quickly, what does all this mean? I think that this is a relatively equilibrated CV reduced chondrite. The homogeneity of olivine is actually consistent with type 3.8 CKs, and that would make this the most metamorphosed CV chondrite of any group. That would suggest that there's certainly a different metamorphic sequence for the CV reduced chondrites and the CK chondrites, but would not rule out a metamorphic sequence between the CV oxidized and the CK chondrites. I think the bigger question right now that is of more interest to me is there other samples like this, or are there other samples like this? And in the weirdest like twist of fate ever, like a week after I finished this project, we were thinking about how do we classify the sample. I got a text message from Mindy Zulu, and he's like, I've got this great anomalous CV chondrite. Would you be interested? And so I read the classification, the description of this sample, 13784, which is classified as a CV anomalous. And the classification here, the description is basically identical to the description of the sample that I just described to you. It has the chromium pore magnetite. It's got the same phthalate content of olivine, but the olivine is nickel poor. Like everything about it is basically identical to this same sample. And so I think we may be seeing samples that are going to represent the first highly metamorphosed reduced CV chondrites, which I think will be really interesting and will certainly help us to better think about this relationship between the CVs and the CKs. And so with that, I know I'm a few minutes over. Just thank you very much for your time. And just I want to thank Alana for her hard work on this project. She's just a rising sophomore, and she did a really, really exceptional job with this project. So shout out to her. And so with that, I'm going to stop sharing here, and I will take any questions that you guys have.
Thank you so much.
I have a question. This is, okay.
Hey, Alan.
Hi, this is.
Go ahead.
Yeah.
Hi there. I enjoyed your presentation. I have a couple things to say. First of all, in terms of petrofabrics, back in 2012, I found that about half the petrofabrics in CVs were in the reduced, the other half was in the Bali type, and none were in the oxidized ones. So Geochemical is wrong about saying that there's no difference between CV oxidized Bali and Allende.
Right, in the petrofabrics.
The second, right. Yeah. Because the petrofabric, I think, is very systematic, because I found none at all in the oxidized group. So I think that's significant, and therefore there really are two groups, like Weisberg pointed out. Okay. Also, you did find chromite in your sample, and that could be sucking up the chromium and maybe other chromite grains, which is why you're finding such anomalously low chromium in the magnetite. I think that accounts for that, and therefore that should not be used as a anomalous criterion necessarily, because I think it's explainable.
Okay. I will say, though, that, Alan, we only found the single grain of chromite. Looking at all of the oxides that we looked at, only one was rich in chromium. So it's certainly possible, but because we only found one, I would wonder about that just a little bit. But you're absolutely right that it could be taking the chromium.
And then just one thing to sort of unrelated about onion shells. Yeah. Since you mentioned that, the most comprehensive study recently is by Scott et al. In 2014, and he for H chondrites, and he went through about 30 of them with the cooling rate. And he found no correlation between cooling rates and petrologic type or argon-argon-oxygen petrologic type. Right. So I think even though there's the consensus of the onion shell because of the a couple of papers by Treloar and things like that, Treloar, but the I think the evidence is weak. Okay. Yeah, certainly. I know the paper that you're talking about, Alan. Yeah, and you've argued that, you know, the changes, the differences in the petrologic types of the CKs are due to shock metamorphism more primarily. So there are certainly other possibilities. I bring up the onion shell because Greenwood suggested that it was an onion shell, and so in trying to assess his single parent body model, because he specifically said it was an onion shell, we kind of started in that direction. But you're right that there is certainly evidence that that may not always be the case.
Mhm.
Okay, I'll shut up for now. Maybe there are other questions.
So Robert Belchels asks, where in the solar system are carbonaceous chondrites formed?
We think that carbonaceous chondrites formed in the outer part of the solar system, so closer to Jupiter than in the inner part of the solar system.
Okay. Bill Spazzeri has a question. If I sent you a high-res photo of a small meteorite I have, which I believe has chondrules, could you give your opinion of what type it is, realizing you can't physically analyze it?
Yeah, sure. You can email me. It's tldunn, so tldunn at colby.edu, and I'd be happy to take a look at it for you. I might not be able to tell you what it is based on a photo, but I can certainly take a look.
Cool. Project Amana asks, sort of excellent talk. Is there a relationship between the metamorphic grade and the peak temperatures of metamorphism experienced by these meteorites?
Yeah, there is. That's a great question. And it's different in different meteorite groups. So peak temperatures in the ordinary chondrites are not the same, for example, as peak temperatures in the CK chondrites, but they do correspond to specific petrologic types. And I think, and Alan would probably actually know, Alan Rubin might know better, but I think the CK chondrites, the peak temperatures are between 800 to 1,000 degrees. I think it's around there, but there is a correlation between metamorphic type and temperature.
John Littleton asks, from some of your initial images, carbonaceous chondrites appear to be an assembly of smaller chondrules. Are gravity and metamorphic heating the mechanisms that cement individual chondrules into a larger carbonaceous chondrite? And in general, what is the intermediate material or the cement between individual chondrules?
So the cement between chondrules is the matrix material. And so we typically think of that as being the cement that holds everything together. There are some chondrules that are like kind of agglomerates of more than one chondrule. And there's one in particular, I think that must be the one you're thinking of, that looks like it might be two. So that is a thing that you see sometimes. I don't think that has been attributed to metamorphism specifically, but I did see some talks at MetSoc last week that attributed these clumped chondrules to heating in particular. So certainly there might be a temperature correlation, but not necessarily. That's not in itself, the clumping is not an effect of metamorphism specifically.
Okay. Do we have any other questions in the chat? I'll give folks a few minutes to finish typing things out. If you'd like to ask a question directly, please let me know in the chat, and I'll ask you to unmute your mic.
Anyway, while we're waiting, this is Alan Rubin again. I just want to tell Tasha that I'm really pleased that she went through and looked at this meteorite in detail, because it's been puzzling me for a long time, and I didn't have the interest to go into the great detail that she did. So I'm glad that she and her student were able to do this.
Yeah, thanks for sending that my way, Alan. I appreciate it. It's been a really interesting sample, and I'm excited that I have another sample that seems to be the same. So it'll be interesting to look at those and do a comparison study.
Mm-hmm.
But
might they be paired?
They might be paired. I did think that. I wondered that initially too. So yeah, we'll see. But I'll take a look. Well, I'll think more about that chromite, and we'll take a look for chromite in the other sample too, and see if we can find more of it. But there just wasn't very much in that last sample, the one I talked about now. Yeah.
Yeah, I just wanted to say as well that this is a really fantastic study to be doing with an undergrad. That's really fantastic work.
She's a really fantastic undergraduate student. She did a really great job, because this is it was a complex project, but she was fantastic. Yeah.
And you should send her our way next summer.
I'm already on it.
Yes.
I'm already on it.
All right. We don't have any other questions in the chat. So it's always hard to get a sense for the audience appreciation in these online talks. I know that's it can be a little bit difficult. So please, if you enjoyed the talk, make sure to thank Tasha in the chat. It was really, really great. I really, really appreciated you coming here today.
Oh, no problem. It's my pleasure. Thanks for the invitation. If anybody else has any other thoughts about this, I would really be happy to hear it if you wanted to send me an email. I'm sure I'll have more conversations with Alan and Ruben about this, but if anyone else has any thoughts, I would be really happy to hear it. It's a very interesting sample, and we'll be looking at it in more detail.
Great. Thank you so much, everyone. Really appreciate you coming out today. And the virtual seminar will continue next week. Unfortunately, I'm on a computer that I'm not normally on, and I've been logged out of all of my various accounts. So I can't get to the schedule from where I'm currently at. But we will send out an announcement about next week's speaker shortly. So thank you so much for everyone for coming, and have a wonderful afternoon.
Thanks, everybody.
Bye.